Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1, 2022, and this is a revision seminar for Probability and Statistics 2. And I've been running around the lecture theatre for the last 15 minutes, getting questions from people. And so there's plenty of things to talk about. And that would require me to put camera on. Okay. Not too bad. Right. Right, well, at the moment, it's going to be a miscellaneous problems session. So let's see how we go. All right, and hopefully we can talk about whatever topics go with that at the time. I just want to ask something. I'm going to pause the recording and ask. Okay. So I'm going to write down some of the problems that I've seen, and we'll talk about them as we go. Okay. So first one I've got is the one on the board behind me, and it says, I wrote it down somewhere. Nope, I didn't. I won't do the one that was in the actual quiz because technically it belongs to the person who wrote it. So can we just think of something else? Number of visitors to the Adelaide Zoo. Day is, let me just pick a number. What do you reckon? I'm going to say 950. On average. What is the probability that the number of visitors on a day is more than 1,500. All right. That's the first problem we're starting with. Yep. I'm not sure what you mean.
So it says calculate the upper bound of the probability. So what is that?
Oh, yep. What is the probability? Not the probability. We can't know the probability. What is? An upper bound for the probability. Okay, so this is an important point. That I'm glad that I accidentally made it. We don't have enough information to know the actual probability, because the only way to know the probability of anything is to know the probability of everything. So we can't know how likely it is to be more than 1,500 unless we know the whole distribution of this number. We need to know what all the possibilities are and how likely they all are. But we can say that the probability can't be any more than something. And so when we say upper bound in maths, we mean a number that is definitely more than the answer. So there is a theorem So you can't know a probability without knowing the distribution. But no matter what the distribution is like, you do know that all the probabilities add up to 1. And so you can get some idea of the probability for any distribution. You make some guesses, and there are 2 theorems about that I know of. There might be more, and one of them, thank you for showing me, is called Markov's inequality. So Markov's inequality says that if x is a random variable which only takes non-negative values, then the probability that x is greater than or equal to a specific number a has to be less than or equal to the expected value of x divided by a. And so this is saying that this probability is less than this, which means this is an upper bound for this. So at first pass, this can be a difficult sentence to process because it has a greater than or equal to and a less than or equal to. But this greater than or equal to is inside the probability. It's telling you about the event that you're finding the probability of. And the probability of that event is less than or equal to this number. You can't be sure what this probability is without more information, but you can be sure it's less than this number. So that's Markov's inequality, apparently. So it seems to me that what we have is information about a random variable. It's a number. It belongs to a day at the Adelaide Zoo. And we have a day at the Adelaide Zoo, and each day would have a different number of visitors. And that number is a random variable. It's not the same every day. And we've been told it's average, so that's the expected value. And we've been finding out a probability that the number of visitors is more than a particular amount. And so that's what this exactly is about. So the full solution would be let x be the number of visitors to Adelaide Zoo on a day. If you're going to have a random variable, you have to tell the reader what the random variable stands for. We know that the expected value of x is 950 according to the information we were told. And so therefore, by Markov's inequality, the probability that x is greater than or equal to, well, we want strictly more than 1500, so I guess 1501, I suppose, because it's a greater than or equal to. It can't be 1500 and a half. Must be less than or equal to the expected value divided by the number I'm thinking of, which is a number. Whatever that number is. Cool, and that's it. When when the answers to a quiz in my uni say plus or minus thing, It's not to say the answer is supposed to have a plus or minus. That's just the machine allowing you to round off differently or accidentally have a difference in the rounding. Are we okay?
Why is it changed from 5 to 10?
Sorry, what's that?
It's one from like X greater than 15.
Mm-hmm. The original, I'm not quite sure what the question means at the moment, but I'm going to say the original question said we want the probability of being more than 1500. And I just need a bit more space. Just give me a second. No, I don't want you to do Markov's inequality yet, just a second. We're okay with this? Okay. And what we want is the probability that X is greater than 1500. That's based on the original question. All right with that? And that's the same as the probability of X being greater than or equal to 1501. Because they said more, strictly more than, didn't they? Okay. So I've translated everything in the question. I've got the expected value. I've got the thing that I'm looking for. And according to Markov's inequality, that is equal to the expected value of X, well, less than or equal to the expected value of X divided by this number. Is that okay? And the expected value of X was 950. Everything all right now? So the probability that X is greater than 1500 is less than or equal to 0.633 to 3 decimal places. Cool. Not a particularly good upper bound. That's pretty huge still. But I guess if you had a really large number, it would become smaller. Makes sense, I guess. You can't have all the big numbers having really big probabilities. Like you can't get the probability getting bigger and bigger as X gets bigger, because then the probability wouldn't add to 1. Like if they're going to be infinitely many possibilities, their probabilities have to get smaller and smaller eventually. Fascinating. So I'm just thinking, if I had a random variable that I knew what the first several probabilities were for the numbers it could be, and then I had this thing and it was less than or equal to the probability you already had, that would tell you that there wouldn't be any probability after that. That'd be cool. Fascinating. Okay, cool. All right. Yep.
But in one of the examples in our course notes, we do include 1500. So we go like 950 divided by
The 1500.
Yeah.
I didn't, because I knew that the number of people couldn't be. I'm not 100% sure. It probably won't make much of a difference in this question because the difference between 1500 and 1501 is not much. But because it was a number of people, it couldn't be anything between 1500 and 1501. But if the random variable was a continuous random variable and it was the amount of time it took between one thing and another, then that could be 1500.7 or 1500.01, in which case being greater than is the same as being greater than or equal to. That's a very important what if question. Well done. Okay. So there's only one other inequality I'm aware of about the probabilities of random variables, and it's Chebyshev's inequality. Is that one that's come up in this course? Might as well talk about it now. Now, is it spelt like this? Does anyone know how it's spelt? Now, always get this wrong. but it says if X is a random variable, with expected value mu and the variance being sigma squared, then the probability that X is that right? Sorry, what's it? Greater than or equal to here? And is this a greater less than or equal to here? Okay. I can't believe I remembered it. Okay. The thing I know about it is, like the picture in my head is that it's just sigma. Just sigma. That makes more sense. But this is a k squared here and a single k there. What's that?
There's also one more formula that says the less than.
Okay, can I just have a look? So in the notes, it also has, just pointing out, in the notes, it also has this. Has that. And this is the opposite of this. Like that, probably these two are opposites of each other. And so their probabilities must be 1 minus each other. And if this is less than this, then the other one has to be more in order to fill up the gap. But this is the one I remember. So the one I remember is this one. And it's in my head, Chebyshev's inequality is about how likely it is to be far away from the mean. So this is saying the probability that the distance between X and the mean is more than K standard deviations. And so this is saying it's further than this from the mean. So in my head, the picture is this. There's the mean. There's 1 standard deviation. There's 2 standard deviations. And so on. And so you'll go K standard deviations. Up and K standard deviations down. And the probability of being outside of this zone that probability is less than 1 over K squared. And so the distribution does whatever it does in here. I don't know what it does. That's the picture in my head. Yep. So saying you can't have more than a quarter, more than 2 standard deviations away from the mean. And you can't have more than a ninth, more than 3 standard deviations away from the mean. So what that means is when you draw a box plot, which has a quarter, which has like half on the outside, the standard deviation's actually got to be less than half the interquartile range, something like that. So yeah, but that's what I'm thinking about in my head here. So there's a distribution here. And I don't know what shape the distribution is, but I do know that the probability of being beyond K standard deviations is less than or equal to 1 on K squared. So I'm sure I could make up an example that goes with that. The length of time A lasts without a puncture has a mean of 2, let's just say 11 months. And a standard deviation of 2 months. Find upper bound for the probability of basketball lasts, give me a second, 2 years or more without a puncture. Length of time basketball lasts without a puncture has a mean of 11 months and a standard deviation of 2 months. Sure, whatever. Find an upper bound for the probability that basketball lasts 2 years or more without a puncture. Okay, cool. So here's my picture. There's 11 months, that's the mean. And 2 years is 24 months. And so I know the probability of being beyond 2, we need to count how many standard deviations that is. So 13, 15, 17. There's a few. I need more, just a second. 13, 15, 17, 19, 21, 23, and there's 25 there. And so that is 1, 2, 3, 4, 5, 6.5 standard deviations. I'll do the proper calculation in a minute. And 6.5 standard deviations down here would get me down to minus something. Okay, so I want the probability of being here. That's what I want. Not 25, sorry, 24. Okay. So Chebyshev's inequality is specifically about the probability of being far away from the mean. Unfortunately, Chebyshev's inequality talks about both sides, but luckily this number can't be negative, and so that's fine. So I've made it slightly more complicated than it needs to be, but that's okay. So let X be a basketball lasts without a puncture. And then the probability that X we want, the probability that X, so in months, we want the probability that X is greater than or equal to, no, 2 years or more, greater than or equal to 24 months. But this could be 24.5 months, that's okay. Okay. All right. I do know if we want to use Chebyshev's theorem, we are going to have to write down, if you want to use Chebyshev's theorem, we're going to have to pitch this as the distance between x and mu. So I've got that the expected value of x is mu, which is 11, and the variance of x is sigma squared, which is 2 squared. Not that we should have just done it as the standard deviation, but that's close enough. Okay, so I know, right. So we know that, let's see, how many standard deviations this is. 24 minus 11, that's how far above the mean it is, and we'll divide by the standard deviation. So 24 is 6.5 sigmas above the mean. All right. So the probability that the absolute value of x minus 11 is greater than or equal to 6.5 sigmas is less than or equal to 1 over 6.5 squared. This is the truth from Chebyshev's inequality. We definitely know this to be true. Okay, I'm just going to work on this. So absolute value being the distance between x and 11 being greater than this. I guess I could have just gone straight to this. It's going to be somewhere between 11 minus this and 11 plus this. Because it's saying how far x is from 11 is more than this. Oh crap, it's not that. Ah, David. It's not that at all. Here's my picture. It's this bit and this bit. And so that's the probability that x is less than or equal to 11 minus 6.5 sigmas, or x is greater than or equal to 11 plus 6.5 sigmas. Right. And that's the probability that x is less than or equal to minus 2. Sigma was 2, wasn't it? Yes. Or x is greater than or equal to 24. And those two things can't happen at the same time, so I can just add the probabilities. And this probability is 0 because it's an amount of time, it can't be negative. Cool. And so therefore I now conclude, sorry, for the paper the wrong way. Therefore I now conclude that the probability of x being greater than or equal to 24 is less than or equal to 1 on 6.5 squared, which is whatever it is. .024 to 3 decimal places. Yep.
So how do I differentiate between applying Chebyshev's and Markov? Because when I read the question, I have an upper bound that I can define. So how do I know which one?
So the extra piece of information you have in Chebyshev's inequality is the standard deviation. So in the Chebyshev's problem, So comparing these two problems, in this one, all I had was the mean. And in this one, I had the mean and the standard deviation. And so I was able to use the standard deviation in Chebyshev's inequality, because the Chebyshev inequality mentions the mean and the standard deviation, whereas Markov's inequality only mentions the mean.
But other than deriving data on your question, how does the question
The question to me doesn't indicate which one. If I was going to do this, I would do them both and pick whichever one was the smallest.
So I did do Markov one.
Yep. And what was your answer for the Markov one?
By 24 months.
Yep. So the Markov one would be the probability that x is greater than or equal to 24 is less than or equal to the expected value over 24, which is 11 on 24, was it?
Yeah.
Which was what?
0.458.
Okay, so we know that this probability is less than 0.458, and we also know that it's less than 0.024. This one's better. This one gives us more precise information. So if you wanted to, you could do both and pick whichever of them is the smallest. But Chebyshev's inequality, I have a feeling, would almost always be guaranteed to give you a smaller number. And also the other thing to note is that Markov's inequality only applies to things that can only be positive, whereas Chebyshev's inequality applies to things that are allowed to be negative as well. So both of these examples, the thing can only be positive. But for things that are allowed to be negative, Chebyshev's inequality applies to that too. So you could have a measurement of temperature, for example, and Chebyshev's inequality would tell you the probability of being greater than a certain temperature or less than a certain probably negative temperature. Yeah. And the final thing is, if you want to know something about both sides simultaneously, then you have to use Chebyshev's, because Markov's inequality only tells you about being greater than something, whereas Chebyshev's tell you being bigger than and smaller than simultaneously. That was a very important question to ask. Those are exactly the sorts of questions you're supposed to ask when you're trying to learn things. It's like, how are they similar? How are they different? How do you decide between them? I love those questions. So thank you. Anyone got anything else to add or ask about Markov's and Chebyshev's or any other inequalities of similar types? Cool. All right. Just gonna. So it turns out that that's not just miscellaneous problems. This is bounds on probabilities. So that's what that bit was about. That's just more for myself. When I put it online, I can tell people when one bit ends and the next bit begins. All right. What else have we got? We've got, yep. Oh, what's that? Oh, well, let's put it down just while we're on it. Do you know what situation that applies in? We're going to have to look that up. Okay. Interesting. All right, so my guess is that this only applies, just based on the way it's written, my guess is this only applies for discrete distributions, and it only applies for discrete distributions that can only be positive. Has anyone got their notes handy? They can search for tail sum. But does it say before that the state? So for y, and it has to be discrete? And it has to be properly positive, or is it allowed to be zero? How interesting. So it's not a tail sum bound, it's just the tail sum formula for the expected value. Fascinating. So this is saying that if you have a discrete random variable that only takes positive numbers, and you find the probability of being greater than or equal to every possible number, is this definitely 1? All right, I'm just making sure. Every possible number, then that's the same as the expected value. What? That's like black magic. Like, what is that? So what? Yeah. So if it had something like this, then we're saying the expected value is the sum of all of these plus 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 the sum of all of those. Of course it is, because this probability gets included 7 times. And so we get 7 times its probability, and 6 times its probability, and 5 times its probability, which is exactly the definition of what the expected value is. Oh, that's so cool. That's so cool. It looks so surprising. So I guess what that means is the expected value is greater than or equal to all of those probabilities. Like, I think you could get from this one 2 Markov's inequality, I reckon. Because all of these numbers are non-negative, right? They're probabilities. And each of them is bigger than the one before. Each of them is bigger than the one after it. Because the probability of being greater than or equal to 2 has got to be bigger than the probability of being greater than or equal to 3. And so I just want to, this is my guess. I just want to guess. I'm not sure if this is going to work. So we know that the expected value of y is the sum from I equals 1 to n. And so that's got to be, so if I use a particular I, like A, for example, then I'm just going to write this down. This is the probability that y is greater than or equal to 1, plus the probability that y is greater than or equal to 2, plus and so on, right? Forever. Once I get to a particular spot, all the ones after this are less than or equal to that. Oh yeah, no, cool. Plus other stuff. So this is definitely less than or equal to the probability of the ones like that, because I've chopped off all the end of the sum, so the answer must be smaller. No, greater than or equal to. Damn it. No, that's right. No, that's a greater than. I thought I had it. I really did. No, it's okay. It's okay. Yes, okay. So this whole sum here is bigger than this just piece of the sum. And we know that this one is bigger than that. because it includes more numbers. So that's greater than or equal to and there's A of them. And so now I've got that the expected value of, nope, don't try and squeeze it in, David. Bad move. The expected value of y is greater than or equal to A times P. And so the expected value of y divided by A must be greater than or equal to the, which is the reverse. Look at that. That's the proof of Markov's inequality for a discrete variable. That's so cool. I would so set that as an exam question if I was the lecturer. I would say, using the tail sum formula for expected value, prove Markov's inequality for a discrete distribution. Ah, yes. What's that? Where? Sorry? Yeah? Oh, yep, thank you. You're right, this entire thing moves there. I don't switch that round. Good move. Thank you for pointing that out. So there would be a different proof of it for continuous distributions. Because this one only works for discrete. That's just, that's just cool. Yeah. Okay. Cool. So I guess this would allow you to basically turn it into Markov's inequality, I suppose. Yeah. Huh. And I guess it says that if you have any one of these, then the expected value has to be more than that probability or equal to. Yeah. Oh. And if you've got a lot of probability at 0, that keeps making the expected value smaller. Because there's not enough room, there's not as much stuff in the other numbers. It's just so cool. Okay. All right. I really want to know what the proof is for continuous distributions, but I don't care that much right now. We can find that out another day. Okay. So I've got some problems here about combining random variables together. So I'm going to run with those and just check on my phone on the photos that I took earlier. And one of those photos just did not work. I need to get that problem you showed me earlier again. I'll get to that later. If we're on this topic, feel free to ask things as we go along that are not things I'm talking about. But one of the problems I have is I'll write it down again. I'll say it out in a minute. Suppose x1 and x2 are independent plus one random variables with parameters lambda 1 equals 1.4 and lambda 2 equals 1.9. Right, here are two probabilities. So we're going to find the probability of x1 plus x2 being equal to 1 and the probability that x2 is equal to 3 given that x1 is equal to 5. Okay, so looking at this question, of these two, which of them is going to be easier to calculate? Yeah? I don't know, you might have different opinions about what counts as easy. The first one? Okay, cool. Cool, I think it's the second one. And I'll tell you why. These two variables are independent, so the value of one has no impact on the probability of the other. So since x1 and x2 are independent, the probability that x2 is 3 given that x1 is 5 is just the probability that x2 is 3. Because it doesn't matter what x1 is, it doesn't make any difference to what x2 does. And that means that I use a Poisson distribution to calculate this. Now, let me see if I can remember this. There's a 3 factorial on the bottom. There's a lambda 2 to the 3, and there's an e to the minus lambda 2. Is that how it goes? And then this is silly. I remember the factorial first. And I remember that it looks, once I've got the factorial, it looks like a piece of the Taylor series for e. And then I multiply by e to the minus whatever. And the reason for that is if you add all of these up, it is e to the plus lambda 2. And so to make it add up to 1, you have to divide by e to the lambda 2. So that's just me knowing. I remember pieces of it and how they're connected. So it comes from the Taylor series. Yeah. Does anyone want to ask more about that? I'm actually going to do this just a second. I'm just going to put a little thought bubble here. E to the lambda 2 is 1 plus lambda 2 plus lambda 2 on 2 factorial squared plus lambda 3 on 3 factorial cubed forever. That's the Taylor series for E. And this bit is here. And if I add all of these up, it'll come up to this. So if I multiply by e to the minus lambda 2, then they'll add up to 1. Which they should if it's a proper probability distribution. And so you end up with this being the probability of 0, and this being the probability of 1, and this being the probability of 2, and this being the probability of 3, and so on. Here you go. I don't know if that's useful or not, but it's the thing that I remember that helps me remember the formula. Of course, if they tell you the formulas, you don't have to waste energy remembering it, but I like the connections between things. Okay, so in our story, we're up to here, and the lambda 2 was 1.9. And so I can ask my calculator what that is. 3 factorial 6, isn't it? Yeah. So I've got 0.171. All right, let's do part A. All right, so I used 2 pieces of information there. One was the fact that they're independent, which was 1 word in the original problem that told me that. And if I didn't know if they were independent, I actually couldn't calculate this probability. It would be impossible. And the other was the formula for the probability probability mass function of a Poisson variable. The other problem asked me to find this. The only way to find the probability of anything is to know the probability of everything. So I need to know what all the options are for x1 plus x2 and how likely they all are. I need to know the distribution of x1 plus x2. So if x1 is, how does your lecturer write the Poisson distribution? Like POIS, PO? If you add 2 independent Poisson distributions, you get a new Poisson distribution. And they're independent. Therefore, x1 plus x2 will also be a Poisson distribution, and the parameter will be 1.4 plus 1.9. That's a theorem. And it makes sense to me because a Poisson distribution counts. I think that's right, isn't it? Yeah, Poisson distribution counts how often something happens in a space or time. And so if I'm looking at a particular amount of time and the average amount of events that happens in that time is 1.4, and if I'm looking at another amount of time and the average amount of events that happen in that interval is 1.9, then if I look across the combined time, then the average should be the sum. Okay. What's that? 1.4 plus 1 would be 2.4 plus 0.9 would be 3.3. So therefore, the probability that x1 plus x2 is equal to 1 is e to the minus 3.3, 3.3 to the 1 over 1 factorial, because that's the Poisson distribution probability formula. Which is 0.123 for 3 decimal places. I'm using 3 because it's convenient. I don't know what your lecturer prefers. I don't think they care. If they do care, then look at what they care. So that's one thing that we need to know. When we think about distributions and you write information about particular distributions, don't just write down the expected value and the variance and the probability function. Write down what happens when you combine them together. So if you combine two normal distributions together, you get another normal distribution if they're independent. I think even if they're not independent, you still get one. Could be wrong. And if you combine two Poisson distributions, you get another Poisson distribution. Yeah. They're the only ones I know off the top of my head. If you square as a standard normal, you get a chi-squared. Did you do the chi-squared distribution in this course? Yeah. Did they tell you how to make a t-distribution? No. Okay. You divide a standard normal by a chi-squared. Okay. No, the square root of a chi-squared, because that's what you do when you make the t-statistic. So, yep. Mm-hmm. So the question is, why didn't I find the probability that x1 was 5? So normally you'd go the probability that x2 equals 3 intersection x1 equals 5 divided by probability that x1 equals 5. That's how you'd normally do it. But I don't need to know the probability that x1 is 5 or even the intersection because the two variables are independent. So this doesn't make any difference to that probability. So it's a bit like when events are independent, the probability of A given B is the same as the probability of A. When random variables are independent, then any event described with one is independent of any event that's described with the other. You're welcome. I have a secret part C that I would like to add. Probability that x1 plus x5 is x2 is 5, given that x2 is 3. These aren't independent anymore. Because I make x1 plus x2 out of x2. And so this variable, this random variable is not independent of the random variable x2 because the random variable x2 makes a difference to what this one produces. And so I would have to do the full working. This would be the probability that x1 plus x2 is 5 and x2 is 3. They do an intersection symbol, don't they? And your lecturer would write this. That'd be this, because that's how you do a conditional probability. Yeah. But if x2 is 3 and x1 plus x2 is 5, that means that x1 must be 2. So because in the land that this refers to, x2 is 3, I can replace that x2 with a 3. And so I get the probability that x1 is 2. And now these two are independent, those two bits of information. And so the probability of the intersection must be the product. And these cancel. Yay. I probably could have done that quicker, actually, couldn't I? Yeah. I have an alternative piece of working for the same thing. If x2 is equal to 3, it's given this information that x2 is 3, I can sub that in there right now and keep it as a conditional. And now x1 and x2 are independent, so I can remove the given x2. That's much quicker than the working I did before. Well, which is like, now what would the, damn it, where is it? $1.4. Which is whatever it is. I can calculate these till the cows come home. How do people feel about the reasoning that I went through there? Both of them use the same piece of reasoning that if I know that x2 is 3, I can sub that into the other one. Yeah. Well, that was fun. How are we doing? Cool, cool. Here's my next example. Independent random variables, all exponentially distributed. With rate 1.5. What's the probability that the minimum is less than 0.01? Or any number you like. So the piece of the core, this is called an order statistic. The minimum. And so if you're looking for a phrase to search the notes for, order statistics would be the phrase. Okay. So I just want to check some things. Already what's happening is that each problem, while it might be about order statistics or be about conditional probabilities, is also about a distribution. So you need to know enough about those distributions to be able to understand what it means to say that it's an exponential distribution. So what's our exponential distribution? It's continuous, I think. And let me just... So an exponential distribution with rate lambda. So y would be continuous. The expected value of y is 1 on lambda. Is that right? And the variance of y also 1 on lambda? Or is it 1 on lambda squared? Okay, so the standard deviation is 1 on lambda. Okay. And the PDF looks like this, as I recall. And I believe, oh gosh, f of y is e lambda, e to the minus lambda. Is that right? Lambda, e to the minus lambda y. Is that right? Cool. Just making sure I know all the things. And the situation in which an exponential comes up is you're measuring the time until something happens in a Poisson experiment. So y measures time until event happens. And that event happens lambda per unit time. Is that right? Lambda per unit of time. Okay. So if it happened, 10 events per minute, the y would tell you, with a lambda of 10, would tell you how long it takes for the first event to happen. If it happened in 10 events per hour and you wanted it in minutes, then then the y would tell you in hours, and so you'd have to convert to minutes. Yeah, and if it happened in 10 every 6 hours, the y would tell you how many 6-hour lots there were. Yeah. Okay. Cool. Just to be sure, that's everything I know about the exponential distribution. I don't know what happens when you add them together. That doesn't seem like a thing to me. Oh, well, I guess if you add them together, that would be the amount of time it would take to get to the second event. Because you'd have to have y1 to get to the first event and then y2 to get to the second event. So it wouldn't be exponential anymore. It'll be something else. There's a name for that. Weibel? Gamma? Oh, I don't know. Might be in one of the later courses. There's a name for the distribution of how long it takes to get to the whatever event. Okay. Cool. So that's everything I know about the exponential distribution. I don't know if any of that's going to be relevant. They haven't asked me about the expected value. Oh, just a second. Y has to be greater than or equal to 0. That's the other thing. It only gives me positive numbers. Okay. So I think the only thing that's going to be useful is this. Actually, this one has a really nice formula for its CDF. Is that 1 minus e minus y? Cool. Just making sure. Okay. The reason I was thinking CDF is I'm wanting a minimum of probability of something being less than something, and that's what a CDF does. Okay, cool. So none of that was strictly necessary, and if you spend all that time in the exam, it probably would be a waste of time, but maybe not. Taking a few seconds to remember some of those things might help you when you get to doing the problem. Okay, so they're independent random variables. They're all exponentially distributed with rate 1.5. So I want the probability that the minimum of y1 up to y5 is less than or equal to 0.01. Is that like y brackets 1? Is that what that's called? Is that how they do it? Yeah, okay. I don't think that matters today, but I just wanted to make sure I remembered the notation. Okay. So this y1 might be any of those y1 to y5, and I don't know which one it is. And different combinations of these will give me a different one of the variables producing this answer. Okay, that's why you can't say it's definitely y1. It could be y any of these. Okay. Well, let me think about it. If any one of them was less than this number, then the minimum would have to be less than that number. Like, this is my imagining. Here's 0.01. And if all the y's were here, in whatever order they were, the minimum wouldn't be 0.01. Like, it would be more than that. And if any one of them was here, the minimum would be less than or equal to that. So the probability of the minimum being less than this is the same as the probability of at least one of them being less than 0.001. Because if none of them are here, the minimum would be bigger. So I reckon it might be easier to talk about the minimum being more than something. The minimum. Can I do that instead? And if the minimum is more than 0.01, then all of them have to be more than 0.01 because it's the smallest one, right? So it's not necessary to do the y1. You could have just left it as the minimum if you wanted, like you don't have to use the symbol for that. This is what I was imagining. Okay, so that means that they all they all have to be simultaneously greater than 0.01 if the minimum is more than 0.01 and vice versa. And because they're independent, intersections of probabilities of intersections become products of probabilities because that's how independent variables work. All right. I'm just going to pause the working at this point and say y1 is exponential with rate 1.5. And so the probability that y1 is greater than 0.01 is, so less than or equal to is 1 minus e to the minus lambda y. So greater than would just be this bit here because it's 1 minus the less than. So just to do the full working of it, it would be because that's the CDF. What I'm imagining here is 1 minus e to the minus lambda y, right? That's what I'm imagining there. So the lambda is 1.5 and the y is 0.01. And so I end up with e to the minus 1.5 times 0.01. I think you're allowed to just know that the probability that y is greater than y is e to the minus lambda y. It's tradition to know the CDF, but in this case, it's actually easier to know the probability of being greater than something. Okay. All right. And they're all the same distribution, right? So the probability that y1 is more than this is the same as the probability that y2 is more than this because this is also an exponential distribution with the same rate. And so I end up with Therefore, the probability that the min of y1 up to y5 is less than or equal to 0.01. That's what I was calculating, which was 1 minus the probability that y1 was greater than 0.01. It's going to be 1 minus that number, and there's 5 of them. They're all the same number. This is that number, this is that number, this is that number, and so I multiplied them all together until I get to the power of 5. Yay. That's right. Yeah. Which is whatever it is. Which says to me that the minimum of a set of exponential distributions is also an exponential distribution. No, not quite. Not quite. Yeah. Yeah. That's so cool. How do we feel about the moves that happened there? Huh. So just want to track that. What if we had one of the probability that the minimum is less than or equal to the number m, I'll call it m. Then the working would have been the same, right? The probability that the minimum is less than or equal to m is 1 minus the probability that the minimum is greater than m, which is 1 minus the probability that all of the yi's are greater than m, which is 1 minus the probability that, you know, y1 is greater than m and y2 is greater than m, etc. Damn it. Which is 1 minus and so that will be 1 minus. I'm going to put an n here instead of a 5, just changing the problem to being n variables instead of 5. And since all these variables are the same, the probability of y2 being more than m is the same as probability of y1 being more than m, which is why I can do this, which is 1 minus like that. That's where I was up to. So look at that. That's the CDF of an exponential distribution. Is rate lambda n. So therefore the minimum of n independent exponential distributions with rate lambda is an exponential distribution with rate lambda n. That's so cool. That's just cool. I don't have anything more than that. So that's like saying you're watching like 5 or however many processes simultaneously? Oh, of course it is. If you're watching 5 processes simultaneously that all happen like once an hour, then the amount of time until the first one of all of the 5, that's the minimum, is the same as the amount of time to all of them. It's just that you're watching 5, so they happen 5 times as often. Oh, that's so cool. So something happens once an hour and you're watching 5 of them, then you should expect 5 an hour for the combination of them. Yay. And so the earliest one that happens, that's the minimum. And so therefore it's the minimum of something that happens it's the earliest one that happens out of something that happens 5 times an hour. That's an exponential distribution. That's so cool. I didn't know that until today. Yay. Now, obviously in your exam, you're not going to do a general proof if you've already done one of those problems. It's a waste of time. I am not the sort of person who ever finished an exam early, and I wouldn't be doing problems that they didn't set in that time. I would be checking that I didn't lose minus signs and stuff like that. But while you're studying, you can do that sort of thing, because now if they set that problem, you can do it, that proof. Yeah. How are people feeling? Are there any other combining random variable sorts of questions that you want to ask? It's okay if you don't. If you think of something, I can always add it to this sheet. I really do want to move on to the last group of things that people asked. Oh, just a second. I lost your problem that you showed me. Was it you, one of you? I can't remember which one I was talking to. You passed me a computer and I wasn't looking at your face at the time. I took a photo of it, but the photo, I moved my phone at the last second and so it came out blurry. Are you able to show me that problem again? All right. So I've only got, what, 15 minutes to go. That went quick. I can go a little longer. So I'm not going to be guaranteed to talk about all of the problems, but I'm going to really try. Okay, let me just have a look and make a decision. Okay. So the problems I've been given there aren't about combining random variables, and yours is about Markov chains. Is that what they call them? And so I can start a new thing. Okay, let me talk about the Markov chains and then I'll see how far I get with the other problems. Okay, right. Markov chain equilibrium problem, probabilities. Okay. All right. Now, normally I would try to make up my own, but I do not trust myself. So I'm going to make one that I'm sure is going to work and copy it from places. I believe this is from one of the tutorials. Is that right? So this matrix has got half, half, 0, 0 along the first row, a quarter, 0, 3/4, 0 along the second row, 0, 1/4, 0, 3/4 along the third row, and 0, 1/4, 3/4, 0 along the fourth row, is the transition matrix for a Markov chain with states 0, 1, 2, and 3. Find the equilibrium probabilities. That's the total problem, right? They did part of it already and then you had to finish it off.
Yeah.
Yep. I just want to do the bit before that as well, just to make sure that I understand and we all understand how to do that. So the idea behind this is that the rows here add to 1, I can see. And so if I have a collection of probabilities of being in the certain states, then when I multiply on the as a row, then if I multiply on the left by this matrix, then that will be the probabilities of being in the states afterwards. So I'm just thinking about this. I've got 0 and 1 and 2 and 3. And if I had all of my probability in position 0, then that would be saying that half of it goes to 0 again, and half of it goes to 1. That's what this row here is saying. That's the row for the first state. And the row for the second state is that a quarter of that goes back to 0, and 3/4 of it goes to 2. And then in state 2, that's this row here, a quarter of it goes back to 1, and 3/4 of it goes forward to 3. And then in state 3, a quarter of it goes back to 1, and 3/4 of it goes back to 2. That's the diagram of how things are relating. So each row tells you where if you're in a particular state, it tells you which state you're going to end up in next. And so if I knew already that the probability of being in each of these 4 states was whatever they were, then multiplying it by this matrix would produce a new probability of being in each of these states. So if I had that, if I knew the probabilities of each state were, this is just an example. So if I knew that it was 50% in state 0 and 20% in state 1 and 0.1 in state 2 and 0.2 in state 3, that adds up to 1, doesn't it? Yes. If I knew that this was the probability of being in each state, I'd know that 50% of the time, I'm expecting 50% of them to be here, and then half of that 50% will be here afterwards, and half of it will be there, and so I'll get 25%, 25%, and then a quarter of this will be here, and a quarter of this, 3/4 of this will be here, and so I'll get extra bits coming from the others, and when you add them all up, it'll give you a new answer. And so if I knew what those probabilities of each state were this, then at the next time, the probs would be the matrix times this. And that's like matrix times row, which is different to how Markov chains are done in Maths 1B. Because in Maths 1, oh no, crap, the P goes over this side because it's a row, damn it. Like that. Like that. You can't put a row on the right-hand side of a matrix, it has to be on the left. So in Maths 1B, the P was on this side, and in this course, the P is on that side. So in Maths 1B, the columns added to one, but probably in statistics 2, the rows add to 1. The Markov chains were in Maths 1B, weren't they? Or were they back in Maths 1A? Yeah, okay. That's what. Yeah, because you had eigenvalues. Yep, gotcha. Yeah. Okay, so that's true. I mean, I don't know what that works out to be, but that's what it would be. The equilibrium probabilities is saying if you've run it for a while and you know, if you have a collection of probabilities of being in each of these states, and then you do it one time after that, it doesn't change the probabilities. Equilibrium means balanced. And so even though I imagine it as a pile of ants crawling around this little thing here, even if there's like 100 million ants in here, and however many are in each of these spots, half of them go here and half of them stay here and a quarter go here and 3/4 go there. Even though all the ants are moving, after they've moved, it's still the same amount of ants in every particular spot. And it's a very like a chemistry thing, chemistry equilibrium. You know, even though there's constant inside your Coke bottle, there's constantly carbon dioxide coming out of the Coke and constantly carbon dioxide going into the Coke. So there's molecules moving continuously. Overall, it doesn't change the concentration. That's sort of the chemistry idea. My chemistry was a long time ago, but you know, that's the one thing I remember. Okay, so at the equilibrium probabilities, which I believe they call pi, don't they? Is that right? Pi for probability. When you do the transition, it doesn't change the probabilities. Like that. Which that means that it's an eigenvector, actually, with eigenvalue 1. So you could find the eigenvectors, but that's not how they do it in this course. What they do is that they multiply this out by this matrix and get 4 equations. And so what you get when you do this I'm just putting them all on one page so I don't have to look. If you're very clever, you don't have to write them down again, which is very important in the exam. So this comes out to be half of pi naught and half of, and damn it, I did it again. No, that's right. No, I'm right. Half of pi naught and a quarter of pi 1. That's what ends up in this spot. And this spot is a half of pi naught and a quarter of pi 2 and a quarter of pi 3. And then this spot is 3/4 of pi 1 and 3/4 of pi 3. And this spot is just 3/4 of pi 2. And this is supposed to be the same as what we started with. And so what you end up with is that this must be pi naught. You don't have to go through all of this writing to get to the right point. I just wanted to show that it really works. You are allowed to just read this and go that many pi naughts and that many pi ones is equal to pi naught. You're allowed to read the rows of the matrix directly if you want. But I just wanted to show where it came from. Well, one of the places it comes from. Okay, so I get these 4 equations in 4 unknowns, which sounds to me like you should be able to figure out what all of the unknowns are. But in fact, we can't. One of those equations is going to cancel out. And we need an extra equation to figure out what all the pi's are. And the extra equation we need is the one that says, well, all the probabilities ought to add to 1. I don't know there was a name for that assumption, but the probabilities have to all add to 1. So you can solve this by whatever method you think is best. You can put them in a matrix and row reduce. You can sub some of them into the others. It looks like I can sub pi 3 into pi 2. Like I can replace this pi 3 with a pi 2. And replace this pi 3 with a pi 2, and then write pi 1 in terms of pi 2. And then from that point, if pi 1 and pi 3 and pi 2 are all in terms of pi 2, I can figure out what pi naught is, and so on. I can figure them all out in terms of pi 2. I much prefer doing it with matrices, but that's just me. So these are the equilibrium equations, is that what they call them? So I could, if I wanted to, rearrange these into something nicer. How did people go about doing this when they did them? Did the lecturer use row operations and stuff? Yeah? They did it by substitution. You're allowed to, I think you're allowed to use whatever method you want. There's no point giving you an entire year of doing row operations in first year and not being allowed to use them now. So I'm going to do both just to show that they're possible. Okay, and then there's this extra equation. We also know that pi naught plus pi 1 plus pi 2 plus pi 3 must be 1. That's the extra piece of information we need to figure it out. So what I'm noticing here is I have that pi 3 in terms of pi 2. I'm going to give them names. So from number 4, I have that pi 3 is 3/4 of pi 2. And what that means is I can sub that into number 3 and it'll tell me what pi 1 is. So I've got 3/4 of pi 1 plus 3/4 of pi 3, which is 3/4, and pi 3 was 3/4 of pi 2. Is equal to pi 2, according to this equation here. So I've got 3/4 of pi 1 is equal to pi 2 minus 9/16 of pi 2, which is 7/16, I guess. Oh, I do not like it, Sam, I am. So now I'm going to have to divide by 3/4, which is the same as multiplying by 4/3. Which is 7/12 of pi 2. Is this similar to the answers they got? I'm really hoping. Okay, so now I know what pi 1 and pi 3 are in terms of pi 2. My last thing is pi 0. I can figure out what that one is from here. So sub into number 1. So number 1 was that half of pi naught plus a quarter of pi 1, but pi 1 is 7/12 of pi 2 is pi naught. So if I subtract half of pi naught from both sides, I'll get this. One pi naught minus a half of pi naught is a half of pi naught. And I'll multiply both sides by 2. And so my pi naught is 7/24 of pi 2. Really hoping I'm doing okay. Please check my arithmetic. Okay, and so what I have is that pi naught and pi 1 and pi 2 and pi 3 are 7/24 of pi 2 and 7/12 of pi 2 and pi 2 and 3/4 of pi 2. And all of those are supposed to add to 1. And that tells me what pi 2 is. Because when I do the sum, that many lots of pi 2 is supposed to be 1. We're going to add this plus this plus this plus this and factorize out pi 2. So I can see that 4 and 12 and 24 all go to 24. So if I multiply both parts by 24, that would do the trick. So I'm going to have 7 plus 7 times 2 plus 24 plus 3 times 6. Lots of pi 2 is 24. I multiplied by the biggest denominator I could see. So multiplying this by 24, I'd give me with a 2 would cancel. And so what's that? I don't like it. 7 plus, well, 3 times 7 is 21, so I can do that. It looks like I can divide everything by 3 at this point, which might make it easier. That is easier. Oh, it's 20. Oh, no, it's not. That's not true at all. 7 plus 8 is 15. It's 21. I am probably wrong. There are so many places I could have been wrong when I was doing this calculation. And since pi 2 is 8 on 21, that means that pi naught is 7/24 of pi 2, which is 7/24 of 8 on 21, which is a 9th. Oh, it's so clean. And pi 1 was 7/12 of pi 2, which is 7/12 of 8 on 21, which is 2/9. And pi 2 is pi 2. We know what that one is. And pi 3 is 3/4 of pi 2, which is 3/4 of 8 on 21, which is 2/7. Ta-da! And I just want to be sure that I've done most of my maths right. These should add up to 1. 1/9. Damn it, come on. Ah. Yay. Okay. And if we were very lucky, we could sub them into these other things and it would still work. So, yeah. How is that? That's one way of doing it. There are others. Cool. Of course, if you're unlucky to not have something like this one that you can sub into the others, then that's harder. The other way is to do it with matrices. So when we were back at this stage, I can subtract pi naught from both sides, and I'll get minus a half of pi naught. And so what I'm going to get is this. And that is a set of linear equations I can solve. Even better, I also have this equation. And so I've got a matrix that I can do this. Zero, 3/4. No, 0, 0. No, that's right. Had that one. That one, 0, 3/4, minus 1, 3/4, 0, 0, 3/4 minus 1, 1, 1, 1, 1, 1. And I can do row operations to get to the final answer from there. But row operations with fractions, of course, so, you know, your mileage may vary. Cool. I'd be multiplying everything by 4 if I were you. I don't want to do it. Maybe the other way is easier. If I had a computer, I could get it to do this for me. That'd be great. Yeah. And you notice this bit, that's P minus I because of the 1A minus lambda I thing from the eigenvalues. Yeah. Well, P transpose minus I. Yeah. Cool. And then you'll get that. And it'll tell you what the answer is. If there are enough zeros, then it might be possible. Cool. And that really is, I think, enough. Need to stop at some point. Cool. I guess my only piece of advice for solving things like that is that you can start anywhere. Like, you need to look at the equations you've got, and a productive way of running this is to write everything in terms of one of the pi's. That's a productive way of running the working for this. Yeah. So, and starting with the equations that only have 2 of them in there, then that you can figure it out. But finding one of them in terms of another one and then subbing that in to eventually get them all in terms of one, it's fine. Pardon me. All right.